Hi, all. Welcome to the 7th session of our Biostats Made Simple webinar series under the SAEM Research Learning Series. My name is Christine Ramdin. I'm a faculty member on the research track at Rutgers, New Jersey Medical School, Department of Emergency Medicine. Today, we're going to continue talking about some of the concepts we were talking about before on basic stats and what tests to use based on the types of different variables there are, as well as go into a little bit about regression models and how to do them in SPSS. Just full disclosure, the regression models that I'm going to show you guys how to do today are not a complete list of the different types of regression models you can do. They're just too much to fill in within, 30 to 50 minutes. So we're going to continue wherever we left off into the next session. Before I start, I'd just like to thank SAEM for allowing me to do this and for Lane and Lynn supporting me and helping me form these efforts and reviewing my slides, etc. So that's all. Oh, also, I'm going to share the slide to this presentation and all of our previous presentations in the chat. The link is in there now, along with the fake data sets that I create so that you guys can do these examples on your own if you would like. Also, I'd like to mention it appears in the last recording. Sometimes when I share my screen, it doesn't show. So since there's only a couple of us here, please feel free to unmute at any time and let me know that you're not seeing my screen, because when I'm sharing my screen, whatever I see, I cannot see what's going on the chat. So if you guys are not seeing something, just please let me know and I'm more than happy to stop and share. Also, feel free to stop me if you have any questions. Otherwise, I'll look for your questions in the chat. Between sharing and unsharing, the messages will get communicated. So thank you all. And with that being said, let's start the presentation. Okay, so this is our agenda for today. We're going to do a recap of some of the things we did in the last webinar. Reason being is that I know we have different attendees every single webinar, and I figure, if we keep on talking about SPSS and keep on familiarizing people with the concepts, you will catch on to it and you may not have to watch every single webinar over and over again. We're going to review the different types of variables because for a lot of the stats analyses we have been talking about throughout the series, the central dogma is that there are 3 types of variables, and these are the certain scenarios where you use these types of variables, and these are the types of regression, and these are the type of statistical tests you would use based on the variable type. So knowing those variables are important, and understanding how, these concepts follow you throughout is also very important. Today, we're going to specifically focus on regression We're going to talk about the different types of regression analyses as a whole, but we're going to focus on the regression analyses used for, scalar or continuous dependent variables. And then we're just going to summarize everything we talked about. So last session, we went over the different types of statistical tests for 3 or more groups of matched, scalar, or continuous data. And what do I mean by scalar or continuous data? Again, these are your variables such as your age, height, temperature, distance, time, anything, essentially numerical variables that can also take on decimal places. What I mean by matched here, I mean data that can be linked between groups or connected over time. Like if we're looking at plant growth from 2020 to from the beginning of 2020 to the end of 2020, we're looking at plant height over time and how it changed. That can be considered almost matched because you're looking at the same plant, but you're looking at its height at different time points. Or we can be talking about the same patients in 3 or more groups. Like if we're looking at patient weights and we're looking at patient weights at 3 months, 6 months, and 9 months, it's the same patient. And you can, if you have identifiers, they can be links between groups. So the tests that are specifically used for the type of scenario when you have 3 or more groups of these type of data, scalar, continuous data, whether it's weights, heights, etc., and you have different measurements of them over time, and you want to determine if there's an overall statistically significant difference in whatever variable you're measuring. For parametric or normal data, you would use the repeated measures ANOVA test. And again, parametric or normal data is essentially when your variables are normally distributed, and you can formally test that using something called the Shapiro-Wilks test. And that's something that could be easily done in SPSS. And, this comes up over and over again, but I'll quickly show you guys how to do it again. So when all 3 of your data sets, 3 or plus your data sets are normal, that's a very unique case. You can use the repeated measures ANOVA test. However, if one of your variables or like one of your time points where you have your heights, weights, etc., if even one of those time points, the data distribution comes back as non-parametric or non-normal, you would have to use the Friedman test as an alternative to the repeated measure ANOVA test. And then lastly, we're just going to talk about, summarize everything we've talked about overall up to this point before we go on to the scalar and continuous dependent regression analyses. So again, just to reemphasize, for matched, repeated, normally distributed data, again, all three of your variables, 3+ variables, have to be normally distributed. Use the repeated measures ANOVA test. If even one of those variables or one of those time points or whatever you want to call it comes back not normal, you use the Friedman test. And in order to test, again, for data normality, you would have to use something called the Shapiro-Wilks test. Generally, Shapiro-Wilks test is used to test normality for smaller data sets. For larger data sets and the literature, I think it's like 2,000 plus data points, you use something called the Kolmogorov-Smirnov test, and this is what the output looks like in SPSS. So in the previous webinar, I had my data sets, I put them into SPSS, and then I conducted the Shapiro-Wilks test following these steps. And these, again, as a reminder, these slides are shared with you in that Google Drive, so you have this at your disposal whenever you're doing this. You run the Shapiro-Wilks test, and it tests your normality for each of the data sets, like each of your three variables. See, I have them labeled here as variable 8, 9, and 10. And the Shapiro-Wilks test, if the p-value is greater than 0.05, that means the data set is normal. If it's less than 0.05, it means the data set is not normal. So here we have each of our three variables and we have their p-values, which is labeled by significance over here. That's your p-value. 0.059 is close, but it's still greater than 0.05. 0.107 is greater than 0.05, and 0.237 is also greater than 0.05. So we're in the unique case that all three of our variables are continuous, they're scalar, and they're normally distributed. So we can proceed in this example to use the repeated measures ANOVA test. And these are the steps for how you would do that in SPSS. You click on Analyze, General Linear Model, Repeated Measures. You define how many levels. You define the name of the variable that's being changed, and you link each variable using the arrow and click OK. I think what I'm just going to do really quick, because I know we're limited for time anyway, but I know that everyone doesn't attend every webinar. I'm just going to share SPSS really quick and just show you guys what it looks like. So for those of you that previously haven't attended or haven't used SPSS, this is what it looks like. And I say this every single webinar, but I'll say it again because we have new attendees. It looks like Excel, but it does not function like Excel. Like, Excel, you can do a lot of sort and data manipulation and stuff. That's outside of the scope of SPSS. SPSS does not deal with that. SPSS only deals with analysis. So actually what I'm going to do here, I'm going to copy and paste my data set that I'm going to use later today in here, just so you guys can kind of see what this looks like. So what I'm doing right now, I'm copying and pasting my data from Excel into SPSS. And if you notice my data, even my ordinal data, such as what I have labeled car type here, not the ordinal data, the nominal data, I have them labeled as numbers. Because whenever you're putting anything into SPSS, SPSS doesn't analyze or it doesn't deal with strings or words. Everything has to be coded in a way for it to understand, to analyze the data. So this is what SPSS look like. And as I told you guys, I just copied and pasted my data here from Excel into SPSS. Each of these data columns represent different things. And what I'm going to do is I'm going to label the columns so we all know what each column stands for. One thing, again, I wanted to mention, like obviously variable 5 and variable 2 are probably nominal variables. They probably represent something. So it's important for you as a researcher to just ensure that you have everything nice and coded and you have a legend for yourself. So you can always refer back to it so you understand what each number stands for. So you see, unlike Excel, where you can just double click and like change the name of the column, SPS doesn't do that. If you double click it, it takes you to something called variable view, if you see at the bottom, where you're allowed to change the names of your columns. And each row here represents a column in the data view. So variable 1 here represents row 1 here in the variable view. So my variable 1 was age, and age is a scalar variable. And that just a quick refresher. I know I'm getting a little bit ahead of myself, but it's good to review it now, so I probably won't have to repeat it later anyway. There are three types, and this is like the central dogma of the whole series. There are three types of variables. There's scalar and continuous variables, which are the same thing. There's nominal variables, and there's ordinal variables. And it's important to understand that because that's the language that SPSS understands. Scalar variables, as I was saying before, is your height, weight, etc. Ordinal variables are like your Likert scale type data. That's like, we use that a lot in med ed research. Like, if we ask the students to rate their satisfaction with the course from 1 through 5, with 1 being like, I'm not at all satisfied with the content presented in this course, and 5 is I'm very satisfied with the content presented in this course, then those are Likert scale type variables because they follow an order. Nominal type variables are like your race, your gender, color, because the variables have categories that represent something. So PSS, like for scalar variables like age, for example, your age doesn't represent anything, but like if you had a nominal variable, which I believe like is variable 2, which is gender, how you could indicate that in SPSS is just by clicking nominal right here, and then you click the values and you tell SPSS what each number represents. So I have for gender, my male represents 0 and female represents 1. So this way you don't lose track of things. So 0 is male and 1 is female. So that's how you keep track of this in SPSS. So let me just continue and label each of these. Let's see, we have car type here, and car type is also a nominal variable. And then I have Honda. It's 1, 2, 3, 4, 5. Part of the reason why I'm just doing this in live time, I could have did it, before the presentation as well, is because I know a lot of people are not familiar with SPSS. So this is just to also make you guys kind of comfortable with how it works and how to input data, etc. So I'm gonna hit OK. My next variable is car length. And car length is a scalar or continuous variable, so we don't have to label anything here. We just go here, we indicate that it's scalar. And just an important note to why it's important to do this in SPSS is because if SPSS oftentimes, if it doesn't detect the correct type of variable per test, it will not let you run the test. You will find that. So it's very important to have everything labeled and everything organized. And then we have our Likert scale variable, whatever that might be, Likert, and that's an ordinal. And we know Likert values also, we can label them with, I think this was regarding ice cream flavors. So I like ice cream a lot, and I don't like ice cream at all. Not at all, a little, moderately, very much. So even Likert scale variables represent something. So just to keep you organized and keep your legend intact, it's good to put values here. The values is not required at all. Like if you tell SPSS the variable is nominal, it would still run the analysis even if you don't put the values, but the values is just here to keep you organized as a researcher. And my last variable is ice cream, whether or not you like ice cream. So this is a binary variable, which is also nominal. So our 0 represents no, and our 1 represents yes. And this is a nominal variable. Alrighty. So these are the variables we're going to use for our regression analyses in this PowerPoint, but right now I'm at the recap. So in the recap, I was telling you guys, how to find data normality, for example, using SPSS. So that's the Shapiro-Wilks test. So you would click Analyze. And here, again, data normality is used for continuous variables. So I have 2 continuous variables here, and that's age and car length. So, with no example, I can just show you how to do that really quickly. So I can hit Analyze, Descriptive Statistics, Explore, and then you can just put however number of continuous and scalar variables in here. You click Plots, you click Normality Plots with Tests, and you click Continue, and you click OK. And here is the output. So what SPSS did here, essentially we ran this analysis to check the data normality for each of these variables, but it also gave me all these nice descriptive statistics, right? For age, it gave me the mean age, the 95% confidence interval, etc. And it did the same thing for car length. And it gave you the min, max, IQR, whatever. And all these things are important because whenever you're writing a paper, you need to report these things. And then it gave me eventually what I wanted was the test for normality. So again, since we have very few data points here, not above 2,000, we're going to look at Shapiro-Wilks test. we see here that the p-value for both age and car length is less than 0.05. So when the p-value for the Shapiro-Wilks test comes back less than 0.05, that means that we failed the test for normality, meaning the variables are not normal. If it was greater than 0.05, that means the variables were normal. And this is important because it helps you determine what statistical tests to use for comparison. In our case, since we're doing a recap on 3+ continuous or scalar variables, we would, look for, if we had 3 variables here, we would look for the p-values for all 3 of those variables. And if you see, in order to use the non-parametric test, even at least one of these have to be non-normal. So immediately when you look at age, you see it's already less than 0.05. Already it fails the test, the criteria for the repeated measures ANOVA test, and you would have to use the Friedman test. So as long as one fails, you have to use the non-parametric alternative. So if you were to do the ANOVA test, if they were greater than 0.05, you would click Analyzed, General Linear Model, and Repeated Measures. And you would just define your variable here. You would tell it how many levels there are. So that would be the number of variables there are. So generally, we talked about 3 in the last one, but ANOVA or a Friedman can be used for 3+ variables, right? So you would put 3, and then the measure name, if it was weight, height, etc. You would click Define, and then, you would select your post hoc test as appropriate, as I discussed in the last webinar. Usually the 2-key post hoc test is generally reported. If you want to compare to any 2 groups of, those 3+ groups that you originally analyzed, you can use the 2-key test. Otherwise, you can select another post hoc test depending on, the criteria you're looking at, whether it's like equal variances, etc. So that's how you do the ANOVA test. And then the steps are actually outlined in the slides, so you guys will have access to that. For the Friedman test, in general, whenever you're doing any non-parametric test in SPSS, whether it's a Friedman test or the Mann-Whitney test, etc., it's a good idea to just go to the non-parametric menu, because half of the time, or more than half of the time, all those tests are right there. You would click non-parametric tests, legacy dialogues. And since we know that we're dealing with 3+ groups, obviously we won't be looking at the 2 samples. We'd be probably looking at the K samples, because remember, it's 3+ groups. And since we were talking in the last PowerPoint about match comparisons, we would hit K related samples. If it was not matched, or if it was like unpaired, we would click K independent samples. But since it's matched or linked data, we click K related samples. And then you would put your variables in here, and you click Friedman and hit OK, and your output will come up. So let me just go back to the slide presentation. And again, I have all these steps highlighted right here so you don't have to forget. And let me see, the next slide, do I have out? Okay, so when you if you have the criteria for the ANOVA set and you run the ANOVA test, this is what the output looks like. In general, you'll find in literature that the p-value for the Greenhouse-Geisser test is the one reported. There's probably different criteria for these other ones, but it's most commonly the Greenhouse-Geisser test is the primary test used to report the results for the repeated measure ANOVA test. And you see that the p-value is less than 0.05, which means that whatever we were measuring, whether it was change of weights over time, whether it was heights over time for those 3+ groups, there was an overall statistically significant change. And to know what that change was, whether it was an increase, decrease, etc., you would have to look at the means or medians as appropriate. Okay, and now this was when I did the Shapiro-Wilks test with the other data set, where at least you see 2 of the variables came back not normal. So obviously in this special case, we would have to use the Friedman test. And then here again, the steps are listed here, and this is what the output looked like. So for the Friedman test, the asymptomatic significance, that's your p-value, is 0.001. So it's telling you at no matter how many groups you were looking at, overall, there was a significant change. And it's up to you as a researcher to find what that change was. And again, as I was explaining before, to test where those changes lie, like if you're looking at 3+ groups, say each group represented a different time point, at 3 months, 6 months, and 6 months, and 9 months. If you wanted to know, well, where did the largest change occur, or where did the change occur? Was it between 3 months or 6 months, or 6 months and 9 months? You can use a post hoc test. For the ANOVA, you can use the 2-key test, etc. But for Friedman's, there's not many tests to find for SPSS. You can always use your 2-sample t-test, or your Mann-Whitney U test, or if appropriate for match samples, the Wilcoxon-Sign-Rank test, or the paired t-test as appropriate to do your post hoc tests. Okay, so we're at the last summary slide here. This is essentially everything we've spoken about in the previous 6 webinars. We have parametric and non-parametric tests for scalar and continuous variables. And these are the tests you would use or the things you would report, the specific, data points you would report for based on whether the data is parametric or non-parametric. So like if your data was normal, you would report mean and standard deviation. If it was not normal, you'd report median and interquartile range. If both your data sets are normal and they're independent, meaning they're not matched, and you're comparing means, you'd use the independent sample t-tests for normal data sets, or you'd use the Mann-Whitney U-test if at least one of those data sets came back not normal. You'd use the pair t-test if you had both data sets that were normal and they could be linked, whether those are students, test results, etc. And you would use the Wilcoxon-Sign rank tests if they were linked, but at least one of those data sets came back to be not normal, the test scores or whatever you're looking at. Again, using the same parallel, one-way ANOVA test for when you're dealing with 3+ sets of data that are all normally distributed and they're independent. So when I say independent, meaning you have like 3 sets of heights of 3 different types of plants, or 3 different sets of patients that are randomized to different arms of trials. You'd use the one-way ANOVA test if all 3 of those groups of data were normal, 3+ groups, or you'd use the Kruskal-Wallis test if at least one of them were not normal. And we just spoke about the repeated measures ANOVA for linked data for 3+ groups, and Friedman test if at least one of those data sets are not normal. So again, we spoke about this before. I'm not going to go into it again, but it's all important to know that the type of regression you use, because there's several types of regressions, as you guys know, depends on the type of dependent variable in that regression. So if the dependent variable is continuous or scalar, you use one type or once. There's a limited number of regressions you could use for that. If the dependent variable is nominal or binary, there's another set of regressions you could use for that. Or if the dependent variable is ordinal, there's another set of regressions you could use. So with that being said, I have all the different types of regression analyses listed in this slide, and all of these are like approximately the most you guys would ever use, unless you're doing some type of really complicated analysis, which is like outside of the scope of this webinar series. These are general that you probably come into contact with and you probably see, and you probably will use a majority of the time. And we're not going to talk about all these today due to the limitations of time. However, we're going to focus on the specific case when your dependent variable in your regression is scalar or continuous. Again, if we're talking about heights, weights, temperature, I don't know, number of miles, etc., those are all examples of continuous or dependent variables. So we do like a simple linear regression when we're looking, and this goes back to grade school, when you have like one X variable and one Y variable. We all have heard of that term, linear regression. We do a correlation and association with exactly one independent and one dependent variable. Then there's the case where you have one dependent variable, but you have multiple independent variables, and you want to see how each of those independent variables are associated with your dependent variable. That's when you see your multivariate or multivariable regression, and we see that in a lot of papers. And then we have also a very special case called general linearized model. And that's a special case when you are looking at 2 dependent variables that are both scalar and continuous with the same independent variable. So you have multiple independent variables, but you want to examine their effects on 2 separate dependent variables. All right, so when you're simple linear regression, you're looking at exactly one dependent variable and exactly one independent variable. Think about your X and Y axis and you're trying to draw a line. You have a bunch of points and you want to draw a line to see if there's an association or a correlation. That's like your linear regression. And these terms keep on coming up over and over again. There's 2 scenarios for even a linear regression, right? So a linear regression is best used for data that can be linearly modeled, right? So you use, I'm sure you guys have heard of your Pearson's correlation coefficient, and this is something that comes up over and over again. That's only used in the case where both your X and Y variable, that is your independent and dependent variable, are normally distributed. Both have to be normally distributed. If at least one of them are not normally distributed, alternatively, you use something called your Spearman's rho coefficient. So there's linear regression, as we all know it is the Pearson's correlation, but there are scenarios where both independent and dependent variables, at least one of them is not normally distributed. You would use something called Spearman's rho. So I'm about to show you guys how to do that in SPSS right now. So the steps are listed out right here. So as I was explaining before, we're specifically talking about scenarios for scalar when our dependent variables and independent variable are both scalar and continuous. So here we only have two variables like that. We have our age and our car length. So we're going to work with those. We want to see if there's a linear association or is there an association between age and car length. And I'm going to hit analyze because we first want to check for data normality, right? So I'm going to hit analyze. I'm going to go to descriptive statistics. I'm going to go to explore. Oh, and we actually already did that. So let's just go back to the output screen for a second to look at the data normality again. So our age and car length, we see both of them. The p-values are less than 0.05. What that means is that both variables are actually not normally distributed. So in that case, we clearly know that we cannot use the Pearson's correlation coefficient because it requires both of those variables to be normally distributed. So alternatively, we have to use something called Spearman's row. In any case, this is how you would do that. You would click Analyze, you would click Correlate, you would click Bivariate, and then I'm going to put age and car length right here. And as you can see here, there's different types of correlation coefficients, right? The Pearson that we just discussed, Kendall's tau, and the Spearman. Spearman is much more commonly used in literature than Kendall's tau. Kendall's tau is also used for non-parametric cases. But, as we just determined, both our variables are non-parametric. And so we cannot use Pearson to evaluate association. We would have to use Spearman. And then we can click the one-tailed or the two-tailed p-value. Full disclosure, the two-tailed p-value is just double the one-tailed p-value. So you can always click two-tailed p-value and divide it by 2. And I'm going to hit OK. And this is our output for Spearman's row. It's telling us that the correlation between the association between age and car length, the coefficient is 0.08. And I'm not sure how many of you guys remember, how association analysis works or the correlation coefficient, but it ranges from 0. Positive associations range from 0 to 1, where 0 is very poorly correlated and 1 is very highly correlated. And specifically with Spearman's row, recall that we're not looking at a linear association because linear associations are measured with Pearson's coefficient. We're generally seeing if there's any association and if there's any increase over time. I'll automatically here, since this is 0.084, we can say these variables are essentially weakly correlated. And the p-value here, that's significance two-tailed, is 0.56. So we can say that there's essentially no association between these two variables. Had this p-value been statistically significant, and remember statistical significance means p is less than 0.05, and generally, if that's the cutoff you select, if that was less than 0.05, we would conclude that there is a significant, statistically significant, but weak association between these two variables, and that association is increasing. Had the negative 0.084, we would have said there was a decreasing correlation, but it's not linear. So again, if our age and car length, if both of them came back to be parametric or normally distributed, we would do the same thing. We would click on Analyze, we would click on Correlate, Bivariate, and instead of clicking Spearman, we would have to click Pearson. And remember, SPSS does not automatically tell you which one to use. You have to know as the user which one to use based on your thing, because we know this is not normally distributed, but if we click Pearson and click OK, it's still going to give you correlation coefficients for Pearson, but that's not correct at all. So that's just for you guys to know. So this is the simple case where you have one independence and one dependence variable that are both scalar and continuous. That's like your simple linear regression and how you would determine what the association is and whether it's significant or not. Did I lose anybody there? Does anybody have any questions before we go to multivariable? Alrighty, so far so good. Let's go to multivariable regression. So again, all these steps are in the slide. So we use multivariate regression when there's exactly one continuous, also called scalar, dependent variable, but more than one independent variable, right? So think about a real world scenario. If we were reading a paper about what factors are associated with plant growth or plant height, and our dependent variable was the plant height, and we had several different independent variables, right? So maybe, temperature was associated with plant height. What else may be associated with plant height? Amount of water given. And let's think about some nominal variables. I don't know, maybe color of light it was exposed to. because, if you're growing a plant indoors, you can expose it to a variety of colors of light. There's like so many things on Amazon these days. You can just buy colored lights and put it on your plants. And color is for an example of a nominal variable, right? So there's different kinds of colors. So like you could have, for when you're doing a multivariate regression, which is a single dependent scalar or continuous variable, you can have many different types of independent variables, which can be continuous or scalar, like I was saying, temperature. It could be nominal, like color, or it could be ordinal. If Likert scale data applied there, you can have that as well. So this is how you would do a multivariate regression in SPSS. We're going to go to the data set. So I'm going to hit analyze because we have all our data right here. Analyze, we're going to hit regression, we're going to hit linear. And our dependent variable here, remember, we're looking at the case where our dependent variable is scalar or continuous. So we're going to hit car length, and here are independent variables. And they could be all nonsensical. They might not have no association with car length, but that's not our job right now. Our job is just to figure out how to do it and figure out what those associations might be. So you see we have a mix here. We have a mix of independent variables of age, which is a scalar continuous variable. We have some nominal variables in here, such as the gender of the person, car type, and whether that person likes ice cream. And we also have an ordinal variable here, which is like our Likert scale variable, which is for rating from 1 to 5, how much do you like ice cream? We're going to hit statistics. We're going to click our R-squared change, descriptives, culinary diagnostics. All of these things help describe the model. So it completely depends on you what you want to check off. Hit continue, and I'm going to hit OK. So this is what my output looks like. So SPSS shoots out a bunch of things that we don't even ask for, or like maybe we did check it off. So it gives you descriptive statistics like the mean and the standard deviation of each of the variables we put in the model. And then let's see, awesome. It does its own correlation analysis, which is not really of concern to us. It provides a model summary. Where's the R-squared? So model summary is important to look at, right? Because it tells you essentially based on the variables that you put in the model, how much can the dependent variable be explained by the independent variables that you put in? And that's important. Why, right? Because we can put in a bunch of random variables as independent variables and check association. And, that may not be relevant to the model, like what we did here. I mean, how is ice cream flavor relevant to car length? That probably doesn't even make sense at all. So it's saying that with our dependent variable, the variance in our dependent variable can be 0.06% of the variance in our dependent variable can be explained by the independent variables that we put in the model, which is not really great. And we don't expect that either because we put in a bunch of random variables for independent variables. But this is essentially a measure of how good your model is at explaining whatever predictor dependent outcome you have. And then the ANOVA test tells us whether that, the model is statistically significant or not. And as we see here, the p-value is not, and we don't expect it to be because we put in a lot of possibly irrelevant variables. But if it was statistically significant, that would essentially be an indicator that your model is a good fit, or it serves the independent variables serve as good predictors essentially of the dependent variable. And, take into the consideration the fact that maybe this was statistically significant, right? We'd move on to look at the meat of our model, which is this coefficient table, which gives you your p-values, which tells you, the significance is your p-values, the association between each of your independent variables with your dependent variable, which was car length in our example, whether they're significantly associated. And if so, what is that association? So we see here that none of the variables, age, gender, car type, ice cream, none of them were statistically significant predictors of car length, which we probably don't expect them to be. However, in the case that one of these were statistically significant, right? Let's say, for example, like say age was statistically significant, p is less than 0.001. Well, how we would interpret that, we would say for every 1 unit increase in car length, the age increases by the age of the person or the age of the car, whatever we're looking at, increases by 0.06. So this tells us, essentially whether the association was statistically significant and by how much the independent variable will increase for 1 unit increase of the dependent variable. So this is why this table is very useful. And this is essentially, what we see in our papers when people are reporting regression results, right? Sometimes they report the beta or not, but they report the p-values, the variable, the p-values, and, the confidence intervals for, the beta value or that unit increase. So that's essentially how you run a multivariate regression and how you interpret its output. So it's fairly simple in SPSS, but it's very important to have your variables appropriate labeled, etc. So I'm going to stop sharing here and go back to the slideshow. Okay, again, everything is outlined here in the slideshow. So again, I was saying that there's a very special case where you have two dependent variables. So for example, instead of just having car length as a dependent variable, we could have car length and age, and we could have had rest of the variables as independent. We could have used a model called the general linearized model. And essentially how you would do that, these steps are outlined here. And this is a more complicated and rare case, so I'm not going to get into too nitty-gritties because we're already over time. I'm just going to show you guys how to do it. So I'm going to click Analyze. We're going to click General Linear Model. So I'm going to click Multivariate. And then you would move your dependent variables here. As I said, this is the unique case when you're doing a multivariate regression and you have two independent variables. You would move your age to dependent continuous scalar variables. So your dependent variables here, and then all your covariates would be any other scalar or continuous variable that's not your dependent variable. And your fixed factors are all of these variables, your nominal and your ordinal variables. And then you would just, click whatever criteria you want, post hoc tests, and you would click OK. And that would run the general linearized model. And again, I'm not going to go deeply into the output of that because, generally that's not really used. It's more of the case when you have one independent and one dependent scalar continuous variable, or you have that case where you have a single dependent continuous scalar variable with multiple independent variables. So I think that'll be enough for now, but in any case, the steps are right here. And now we're just going to summarize everything we talked about today. So, when we have matched analyses for 3+ groups of scalar or continuous data or ordinal data, this is what we discussed in our recap. We use repeated measures ANOVA where all 3 of your data sets are normally distributed. And we use Friedman tests when at least one of those variables are non-normally distributed. And again, matched means the data are linked if you have the same patients or you're checking same patients throughout your 3 groups and you're measuring weights or something at different time points, or you're measuring plant heights at different time points. That's an example of a matched analysis. Again, widely speaking, the type of regression analysis you use depend on the number of variables you have and the type of dependent variable. Today, we specifically discussed this case where you have a scalar or continuous dependent variable or variables, because we have the general linear model when you have the very unique case that you have 2 dependent variables. And actually, this goes into the next session. But like when you have your output and you have the exponent beta, which we didn't have in this slide, but it'll be in the next slideshow, that's actually your adjusted odds ratio. So it actually tells you how powerful your independent variable is at predicting your dependent variable. But here we were just looking at more of a linear association. So we were looking at beta in terms of unit increase. So that's essentially how we interpret the output. We look at the p-values of the regression as well as, the unit increase based on the beta provided in that regression table. We also have to remember to look at model fit, because that's important to telling us how good our independent variables are at predicting our dependent variable. Because, in an ideal world, all the time we won't have all the variables that we necessarily predict our dependent variable. So that's pretty much what I have to offer today. Are there any questions? Are the Pearson and Spearman tests specifically for correlation, while other tests are used for regression? So think of Pearson correlation as a linear regression, right? Because remember, when you do a linear regression, we kind of learned it like this, right? In grade school, high school, whatever. When we do a linear regression, what are we thinking of? We're looking at the association between an independent and a dependent variable, right? So it is a regression. It's called a linear regression, but the coefficient that is a result of that regression is called the Pearson correlation coefficient. However, this is a specific case for when both your dependent and independent variables are normally distributed. When they're not normally distributed, then you use the test called Spearman's rho. So I would say that when you use the correlation coefficient called Spearman's rho, it's not usually called a regression, but that's essentially what it is. It's associating an independent and dependent variable, but it's not a linear association. It's just like what they call, it's like almost like a monotonous curve. You want to see if there's a general increase or decrease over time. Does that answer your question? Awesome. Thank you so much.